Hello everyone, my name is Nilanjan Chakraborty and today I will be talking about our paper on screw linear interpolation for point-to-point path planning. This is joint work with my former students Anik Sarkar and Anirban Sinha. We are interested in developing motion planning algorithms for manipulation tasks, which essentially introduces task space constraints in motion planning. The figure shows an example of transferring a glass of water from an initial location to a goal location. To avoid spillage during movement, the orientation of the glass should not change while moving it to the cup. While pouring, the position of the glass should not change. As you can see, this manipulation task imposes certain constraints on the motion path of the object being manipulated. These constraints are called task space constraints. The goal of this paper is to present a motion planning algorithm that can deal with task space constraints in a simple and efficient manner. Note that the object may also have to avoid obstacles during this task, as shown here. However, obstacle avoidance is not the focus of this paper. Let me first introduce our problem formally. We are given the initial and the final pose of the end effector in the task space or SE3, which is the group of rigid body motions. We are also given the initial configuration of the robot in the joint space. Our goal is to compute a sequence of joint angles such that the end effector reaches the goal pose, that is f of theta m equal to gf, where f here is the forward kinematics map. The joint limit constraints, if there are any, are satisfied. The collision avoidance constraints are satisfied, and the constraints on the end effector path during motion are satisfied. In this paper, we'll focus on reaching the goal while ensuring that the constraints on the end effector path is satisfied. The joint limit constraints can also be handled within our framework, although we'll not talk about it explicitly. The task space or the space of rigid body motions AC3 form a group, and it is not a vector space. So the constraints that we will be considering on the end effector path will form subgroups of AC3. Let us look at some examples of such subgroup constraints. Some common subsets of AC3 that form subgroups are Rn, the set of pure translations, SO2 or SO3, the set of pure rotations, AC2, the set of all planar motions, SO2 cross R1, the set of all cylindrical motions, and H1, the set of all screw motions. Example tasks include opening a drawer, which is an example of motion restricted by a prismatic joint, opening a hinged door or a valve, which are examples of motion restricted by revolute joints, opening or tightening a bolt with a wrench, or screwing or unscrewing a bulb, which are examples of screw motion. In summary, for planning motion for manipulating human-designed objects with mechanical joints, the motion of the end effector is restricted to a subgroup of AC3. There is a vast amount of related work in motion planning, so I will not really do any comprehensive review here, but I will just touch upon some high-level characteristics of motion planning algorithms that are required for understanding this work. There are three spaces that are associated with motion planning: the workspace, which is a subset of our 3D world, the joint space, which is the set of all joint angles of the robot, and the task space, which is the set of all end effector positions and orientations. We can go from the joint space to the task space by using a forward kinematics map, which is a nonlinear mapping. We can go from the task space to the joint space using an inverse kinematics map, which is a nonlinear multivalued mapping. And we can also go back and forth between the tangent spaces of the task space and joint space using a differential kinematics map. As I stated before, usually we know an initial pose in the task space and a final pose in the task space, shown by the red and the green dot here. We also know the corresponding initial pose in the joint space. In joint space-based planning, we use the inverse kinematics map to find the corresponding goal configuration in the joint space. We can formulate the motion planning problem in the joint space in a rigorous way without any reference to the task space. Much of the work in motion planning has focused on joint space-based approaches, and during planning, one usually does straight-line interpolation between two joint space configurations. However, the task space constraints leads to nonlinear manifold constraints on the joint space because the forward kinematics map is nonlinear. So linear interpolation in the joint space does not give paths on the manifold. So it becomes quite complex to deal with task space constraints in joint space, although there have been several efforts in this direction. On the other hand, task space-based motion planning techniques needs to go back and forth between the task space and the joint space. And usually we go from the task space to the joint space using the inverse differential kinematics map. The general class of techniques that are used to move from the task space to the joint space are known as resolved motion rate control. There are many different interpolation schemes that are used during planning. Two particular interpolation schemes that would be of interest to us are the screw linear interpolation and the linear interpolation in parametered space, where that AC3 is parametrized by a 7x1 vector with 3 Cartesian coordinates for position and a 4x1 vector of unit quaternion for orientation. We will discuss these two techniques in more detail later. In these methods, task space constraints can be handled by using priority-based task Jacobians. This implies an implicit order on the importance of a constraint and hence soft satisfaction of some constraints. One of the earliest approaches for motion planning is based on screw linear interpolation. In this approach, SCLRP was used for obtaining a path in SE3 and a pseudo-inverse of the Jacobian was used to get the corresponding path in the joint space. However, most modern task space-based approaches do not use screw linear interpolation. They use linear interpolation in parametered space. One common argument against using SCLRP is that the screw linear interpolation gives paths that are not intuitive to an user or operator. This critique was made in the context of pick-and-place operations of objects. The key contribution of this paper is to show that using screw linear interpolation has some inherent advantages when dealing with task space constraints. We can ensure that common motion constraints that arise in manipulation can be satisfied without explicitly considering them. In particular, we prove that when the motion of the end effector is constrained to a subgroup of SE3, if the two end poses are in the subgroup, then the whole path will be in the subgroup. Consequently, we can show that any task constraint that can be decomposed into a sequence or combination of motion subgroup constraints can also be satisfied without explicitly enforcing them, just by choosing intermediate waypoints in SE3. In the rest of the talk, I will not delve into the technical details of the theorems and the proofs. I will present some details about our approach and show some practical applications. I will now give a quick primer on screw linear interpolation. Let D0 and DF be two poses of the end effector. Here T is the relative translation between the two poses, and there is also a relative rotation. According to Chesel's theorem, there is an axis in space denoted by U here, such that rotation about the axis by an angle, which is 2 alpha here, and translation along the axis by an amount, which is D here, moves the end effector from D0 to DF. This motion is called the screw motion. The screw motion in SE3 is the analog of the shortest path motion in the Euclidean space. It is a 1 degree of freedom motion. In our paper, we have used the unit dual quaternion parametrization of SE3 to perform the screw linear interpolation. The choice of unit dual quaternion is mainly because of efficiency. You could also have done screw linear interpolation with the 4x4 transformation matrices. For any choice of the parameter tau, we get a pose obtained by rotating from D0 by an angle of tau alpha about U and translating along U by an amount of tau D. One key feature of using screw motion for interpolation is that the motion generated is independent of the choice of the coordinate frame. Consider the example of turning a door handle, which is hinged at this point. The motion of the handle is purely rotational because there is a revolute joint here. If we choose the end effector initial pose and the goal pose as shown here, screw linear interpolation will give intermediate poses on the circle, which corresponds to pure rotation about the hinge. So the constraint that the hand should move on a circle because it is operating a hinged object is satisfied without any explicit enforcement, just by choosing the initial and the final pose. However, if we do linear interpolation in parametered space, using the same start and the goal pose, we'll obtain a path like this, which does not respect the constraint that the hand is operating a hinged object. As I indicated before, we are using a two-step iterative algorithm for motion planning. The starting pose in the task space is shown by the red dot here, and the starting pose in the joint space is shown by the red dot here. The green dot here shows the goal pose in the task space. In the first step, we do screw linear interpolation to generate the blue dot. The corresponding joint space configuration is generated by resolved motion rate control. Since this mapping is an approximate mapping because we have discretized the differential kinematics, we have to map this blue point back to the task space, and we actually reach this yellow dot here when we move to the blue dot in the joint space. Now from this yellow dot, we again continue the same process till we reach the green dot or the goal configuration. Let us now look at some experimental results. We'll first look at planning for the liquid transfer task. The liquid pouring task has two sequential constraints. First, the end effector orientation should not change while moving the glass. Second, the end effector position should not change while pouring. To generate the motion plan to satisfy these constraints, we use an intermediate pose G with the same position as the final pose and the same orientation as the initial pose. And then we use screw linear interpolation between G0 or the initial pose and the intermediate pose G, and again between G and GF. The resulting motion plan that we get satisfies the constraints along the path. Thus, just by choice of an intermediate waypoint and screw linear interpolation, we ensure that the path constraints are satisfied. We will now look at a planning problem for a dual-armed manipulation task for serving a drink on a tray. In this task, there are two constraints that have to be imposed on the end effector motion simultaneously. First, the end effector motion has to be constrained such that the tray is always kept horizontal. Second, the relative position between the two end effectors should always be constant so that it doesn't drop the tray. In this case, we generate the motion plan by using sklurp independently for the two arms with the same interpolation parameter, and we select the initial and goal hand frames as follows. We ensure that the relative pose between the two hands is the same at the beginning and at the end, and also for each hand the orientation of the hand is same at the beginning and at the end. Note that for planning in joint space, the third space here is 14-dimensional because each arm has 7 degrees of freedom, and each one of these constraints are nonlinear constraints in this 14 degree of freedom third space. So the planning problem in joint space is quite complicated. However, here just using screw linear interpolation and proper choice of the initial and final frames of the two hands, we satisfy both these constraints for free. Let us now see some experimental results for the two applications that we just described. On the left, we see one instance of the water transfer experiment, and on the right, we see one instance of the water serving experiment. To conclude, we showed both theoretically and experimentally that the use of screw linear interpolation in task space-based motion planning ensures that either sequence or combinations of task space constraints that are subgroups of the rigid body motion group can always be enforced without considering the constraints explicitly. There are many applications in manipulation where such constraints arise. For example, manipulation of articulated rigid objects like opening doors, opening drawers, screwing or unscrewing light bulbs satisfy these motion subgroup constraints. In the future, we would like to incorporate collision avoidance constraints within this framework and also incorporate kinesthetic human demonstration within the motion planning framework. Furthermore, we are also using this motion planning algorithm for manipulation of objects by exploiting contact with the environment instead of pick and move types of tasks that we have seen here. Some preliminary results on incorporating collision avoidance within our motion planning scheme is shown in this video. We use a linear complementarity formulation of the kinematics to avoid collisions in this case. Thank you for your attention, and if you have any questions, please reach out to me at the following email.